So if you took the piston and you nailed the piston so it cannot move, and you put it on a hot plate, P dV part will vanish because there is no delta V. That's the way of heating it is called delta Q. Another thing you can do is you can thermally isolate your piston, so no heat can flow in and out of it, and you can either have the volume increase or decrease. If the gas expanded, delta V is positive, and the P delta minus P delta V is negative, and the delta U will be negative, the gas will lose energy. That's because the molecules are beating up on the piston and moving the piston. Remember, applying a force doesn't cost you anything, but if the point of application moves, you do work. And who's going to pay for it? The gas. It will pay for it through its loss of internal energy. Conversely, if you push down on the gas, delta V will be negative, and this will become positive, and the energy of the gas will go up. So there are two ways to change the energy of these molecules. In the end, all you want is you want the molecules to move faster than before. One is to put them on a hot plate where there are fast-moving molecules. When they collide with the slow-moving molecules, typically the slow ones will move faster and the fast ones will move slower, and therefore there will be a transfer of kinetic energy. Or when you push the piston down, you can show when a molecule collides with a moving piston, it will actually gain energy. So that's how you do work. So this is the first law. So let us now calculate the work done in a process where a gas goes from here to here on an isotherm. Isotherm is a graph of a given temperature. So this is a graph, P times V equal to constant, because PV equal to nRT. If T is constant, PV is a constant, it's a rectangular hyperbola. The product of the x and y coordinates is constant. So when the x coordinate vanishes, the y will go to infinity, y coordinate vanishes, x will go to infinity. So you want to take your gas for a ride from here to here. Throughout, it's at a certain temperature T. What work is done by you? That's a very nice interpretation. The work done by you is the integral of P dV. But what is integral of P dV? That's P, and that's dV. P dV is that shaded region. In other words, if you just write P dV, it makes absolutely no sense. If you go to a mathematician and say, please do the integral for me, can the mathematician do this? You have to know the function. If you just say P, you'll say maybe P is a constant, in which case I'll pull it out of the integral. But for this problem, because PV is nRT and T is a constant, P is nRT divided by V, and that's the function of V that you would need to do the integral. And if you did that, you will find it's nRT. All of them are constants. They come out of the integral, dV over V, and I integrate from the initial volume to the final volume. And you guys know this is a logarithm. And the log of upper minus log of lower is the log of the ratio. And this gives me nRT log V2 over V1. By the way, I mentioned it now. I don't want to distract you. But suppose later on I make it go backwards like this part of the way. The work done on the going backwards part is this area, but with a minus sign. I hope you'll understand. If you go to the right, the area is considered positive. If you go to the left, the area is considered negative. If you do the integral and put the right limits, you'll get the right answer. But geometrically, the area under the graph in the PV diagram is the work done if you're moving the direction of increasing volume. If you would decrease the volume, for example, if you just went back from here, the area looks the same, but the work done is considered negative. You don't have to think very hard. If you do the calculation going backwards, you will get log of V1 over V2. That will automatically be the negative of log of V2 over V1. Very good. So this is now the work done by the gas. What is the heat input? The heat input is the change in internal energy minus the work done. Let me see. The law was delta U is equal to delta Q minus delta W. Yeah, let's go back to this law. In this problem, delta W is what I just calculated, nRT whatever log V2 over V1. What is delta Q? Yes. This is what I told you is a fact that people do not constantly remember, but you must. This gas did not change its temperature. Go back to equation number, whatever I wrote down, U equals 3/2 nRT or something. T doesn't change, U doesn't change. That means the initial internal energy and final internal energy are the same, because initial temperature and final temperature are the same. So this guy has to be 0. That means delta Q the same as delta W in this particular case. So yes?
But if Q is equal to MC delta T, wouldn't that imply that there's a change in temperature?
When you say MC delta T, you got to be careful what formula you want to use. This question is the following. You're telling me you put heat into a gas, right? And you say temperature doesn't go up. How can that possibly be? I always thought when I put heat into something, temperature goes up. That's because you were thinking about a solid where if you put in heat, it's got to go somewhere, and of course temperature goes up. What do you think is happening to the gas here? Think of the piston and weight combination. When I want to go along this path from here to here, you can ask yourself, where is the heat input and where is the change in energy, and why is there no change in temperature? If you take a piston like this, if you want to increase the volume, you can certainly take off a grain of sand, right? If you took the grain of sand, and the piston will move up, it will do work, and it will cool down. But that's not what you're doing. You are keeping it on a hot plate at a certain temperature so that if it tries to cool down, heat flows from below to above, maintaining the temperature. So what the gas is doing in this case is taking heat energy from below and going there and working against the atmosphere above. It takes in with one hand and gives out the other without changing its energy. So when you study specific heat, which is my next topic, you've got to be a little more careful when you talk about specific heats of gases, and I will tell you why. There is no single thing called specific heat for a gas. There are many, many definitions depending on the circumstances. But I hope you understand in this case, you've got to visualize this. It's not enough to draw diagrams and draw pictures. What did I do to the cylinder to maintain the temperature and yet let it expand? Expansion is going to demand work on part of the gas. That's going to require loss of energy unless you pump in energy from below. So what I've done is that I take grain after grain so that the pressure drops and the volume increases. But the slight expansion would have cooled it slightly, but the reservoir from below brings it back to the temperature of the reservoir. So you prop it up in temperature. So we draw the picture by saying the gas went from here to here, and we usually draw a picture like this and say heat flowed into the system during that process.